Good morning, everyone. So this is lesson 1.1, rates of change for grade 12 calculus. Okay, so for calculus, introduction to limits, we're going to start with rates of change from advanced functions. We're going to start with talking about the average rate of change as well as the instantaneous rate of change. Okay, so many relationships involve dependent quantities like surface area of a sphere varies with the length of the radius, or the volume of a cylinder varies depending on its height. We often are interested in how rapidly the dependent variable changes. So how rapidly will the surface area of a sphere change if there is a change in the independent variable, which in our example is the length of the radius. So in other words, as the length increases, think about a balloon. Okay, as the length of the radius increases, imagining a perfect circular balloon or a perfect spherical balloon, how does the surface area of the balloon increase? Okay, so with average rate of change in advanced functions, we talked about, in grade 9, we talked about the slope formula, which is rise over run. Okay, it's essentially the same concept. Okay, so if we look at this example, the average rate of change, so this point right here will be, let's call this, no, let's start here. Let's call this x1 and y1. And for this particular example, this point is 0, 0. Okay, and let's call this point x2, y2. Okay, or in other words, 0.24. Okay. Now, to use proper function notation, we can also say that this point right here would be x2, okay, and f of x2, which essentially means the same thing as y2. Okay, this is a function of x. Same can be said with this point down here, x1 and f of x1. Okay, so using proper function notation, we're going to look at what the average rate of change is. So we're going to call this AROC, okay, for average rate of change, is equal to, so if you look at the two given points there, okay, and we connect those 2 points, so we're looking at the rate of change between those two dots of this parabola. Okay, by connecting those two dots, you can see we have drawn a dotted line. So to find the average rate of change, which is rise over run, okay, so we're going to say y2 minus y1, or we can say, so y2 minus y1, or we can say f of x2 minus f of x1. Okay, so it's y2 minus y1 over x2 minus x1. Okay, so that is our average rate of change. Now for this particular example, let's use the values that we are given. Okay, so which in this case will be, well, what's f of x2? It's our y2, in other words 4. So 4 minus, what's our y1? F of x1, y1, 1, 0. 4 minus 0. Subtract, or over, x2, okay, which is just 2, minus x1, which is just 0. So 4 minus 0 is 0, 2 minus 0 is 2, 4 divided by 2 is 2. So in this case, our average rate of change is just 2, and then we should have units, but we clearly don't. But let's say, for argument's sake, let's say this was length in centimeters, and let's say this was volume, so centimeters cubed, let's say, okay, then we would say 2 centimeters per centimeters cubed, okay, or sorry, other way around. So 2 centimeters cubed per centimeters. So the surface area, it's early. It's not centimeters cubed because centimeters cubed would represent volume. Oh, and that is the example we're using. So never mind, we're good. Again, this is just for argument's sake. Okay, I just completely made this up on the spot. But in other words, it's your 2 y values per x value. Okay. Now, so if we were told to find, for example 1, told to find the average velocity. So we've got a pebble that is dropped from a cliff. Okay. So let's say this is a cliff. You've got a pebble that's being dropped. Okay. From a cliff, height of 80 meters. Okay. At t seconds, it is s meters above the ground, where st is represented by this formula. So we want to find the average rate of change. So let's pretend this is when time is 0, and it takes 4 seconds for it to fall into the water, let's say. Okay? So we want to know what the average rate of change is between time 0 and time 4. So in other words, we want to find the slope of that line. So the average rate of change between those 2 points. Okay? So now, let me just draw a cleaner parabola. Okay. So again, doesn't have to be a perfect parabola. This is just a really rough drawing. Okay. But I do know I want to find the average rate of change between this point and this point. Okay. So up here we'll have an x value of 0 because that's at time 0. And that's an x value of 4 because that's at time 4. Okay. Now, how do we find the corresponding y values? All we do is take our given times. So in this case, oops, it's my mistake. We're not looking for time 0. We're looking for time 1. So between time 1 and time 3. Okay. My mistake. So let's backtrack. Get rid of that. Get rid of that. Okay. So we're looking at time 1 and time 3. So we're looking for the rate of change between 1 second and 3 seconds. Okay. So let's draw again. Yeah, that's a terrible line, but you get the idea, connecting those two. So we are not looking at 0 to 4. Okay. That was just the interval given to us. Okay. We're looking at specifically from time 1 to time 3. So at time 1 and time 3, what are our corresponding y values? Okay, so well, time 1, all we do is we plug it in to this formula. Okay, so plugging it in, we will get, so let me just load up Desmos here. In future videos, I'm going to have a scientific calculator loaded up on the screen, so it's easy for you to see what I'm plugging in. But for whatever reason, the scientific calculator is not working today, so it's not as a part of this video. So I'm just going to use Desmos. Okay, so I'm taking the formula, so 80 minus 5 t squared. Okay, so well, what's t? Well, we're trying to find out what the distance is at time 1. So I just replace that with 1, and I get 75. So which means the corresponding y value, or f of x1, is 75. And then at 3, it is 35. Okay, so our average rate of change here is simply y2 minus y1, 75 minus 35, divided by x2 minus x1, 1 minus 3. Okay, and yes, the order matters. So y 75 minus 35, since I started with 75 up top, okay, and just start with 1 underneath. You can reverse it and go 35 minus 75 and 3 minus 1. That's fine as well. Okay. So we have 75 minus 35, which is 40. 1 minus 3, which is negative 2. 40 divided by negative 2 is negative 20. Okay. Well, negative 21. So negative 20, so it says S represents S meters above the ground. So the pebble is falling at a rate of negative 20 meters per what? Time is in seconds, so per seconds. Okay, so between 1 second and 3 seconds, it is falling at negative 20 meters per second. For part B, it's pretty much the same thing. Find the average velocity between t equals 1 and t equals 1.5. So now we are looking at, let's use a different color for this. let's use, what color have I not used? Let's use pink. So our average rate of change would be between 1 and 1.5. So we're looking at between 1 and 1.5, so somewhere here. Okay, so now we're trying to find the rate of change between those 2 points. Same idea. Okay, so first off, I need to find out what S of 1 is. Okay, wait, I already know what that is. It's 75. So 1 and 75, because we already did that right here. Okay, now we got to find what S of 1.5 is. So let's go back to the formula, the given formula, which is 68.75. So this gives us 68.75. So at 1.5 seconds, it is 68.75 meters above the ground. So now we go again y2 minus y1. Okay. So y2, we're going to go 68.75 minus 75. Okay, and then 1.5 minus 1. Okay, so then 68.75 minus 75. You know what? Let's just save time. And then 1.5 minus 1 is 0.5. So negative 12. So negative 12.5 meters per second. Okay? So which means that between 1 and 1.5, it's falling at a rate of negative 12.5 per second. Now let's see if this makes sense for a second here. Between 1 and 1.5 seconds, it's falling at a rate of negative 12.5 meters per second. Between 1 and 3 seconds, it's falling at a rate of negative 20 meters per second. So does it make sense that for this bigger interval between 1 and 3, it's falling at a faster rate? Sure it does, because of something called gravity. Yeah, so between 1 and 3, it's obviously picking up momentum. So the gravity is has a bigger impact. So then between 1 and 3, it's falling at a faster rate than it is at the average velocity is higher between 1 and 3 than it is between 1 and 1.5. Okay. So for a lot of these examples, it's pretty much the same thing. Okay. I'm going to attach the solutions to this on D2L, but I don't think I need to go through these examples in a video. It's the exact same thing, but I will post these solutions. If you want me to go through these in a video, or you want to meet and go through it, I'll be more than happy to. I do want to try to keep these videos short. Okay, especially since we're going to get into much harder topics. The average, okay, now moving on. The average rate of change is the slope of the secant to the curve. Okay, so what does that even mean? Well, what is a secant line? We actually drew a bunch of them already. So this line right here, this is called a secant line. Okay. The line that connects 2 points. This line right here is called the secant line. Okay, so we've done that here. We drew a secant line here between these two dots, the blue line. We drew a secant line here, the red line between the two. Okay, that's called a secant line. Now the slope of that secant line, which is exactly what we've been solving for, the slope itself of the secant line is called the average rate of change. Okay, now what about the instantaneous rate of change? Instantaneous rate of change is the slope of the line at an instantaneous point, or example, the tangent line. Okay, so it requires using 2 points. We must choose 2 points that are very close to one another. What does all of that mean? Okay, well, let me show you. Give me 1 second here. I was taking a look at the time. Okay. You know what? I'm going to record a second video talking about the second half, okay? Just so I can keep these videos under 15 minutes, okay? All right, so I'll see you in the next video. I'll talk about the instantaneous rate of change.